The lesson on combination of capacitors is quite similar to the lesson on combination of resistors, and that is something that we're going to talk about in this episode of Physics is Easy with Mr. Jesse. In this slide, we could see the two combinations of capacitors, so they could either be connected in series or in parallel, just like a resistor. So if we're going to draw the schematic diagram for capacitors in series, so it's going to look like this. We have the two capacitors, and we have here the voltage source. On the other hand, we could draw this combination of capacitors in parallel in this manner. So we have C1 here, this is our C2, and here we have our voltage source or the battery. Now let's look into capacitors in parallel. So if you recall, in resistors, the terms that we are going to the terms that we focused on are the following. We have total current, we have total voltage, and we also have the total resistance. Now if we talk about capacitors, total current is very similar to the total charge. After all, we define current as the flow of charge. Total voltage is still total voltage when we talk about capacitors, and instead of total resistance, in this case we will have the total capacitance or the equivalent capacitance. Now, for capacitors that are connected in parallel, charge and current is actually quite the same. So in resistors, total charge is just equal to I1 plus I2 plus I3, rather total current is I1 plus I2 plus I3. And when we talk about capacitors, total charge is Q1 plus Q2 plus Q3. Also, total voltage is the same as that of parallel, so it's the same for all the voltages in our capacitors. So therefore, in this case, C1 and C2 will have the same voltage as that of the battery, or equal to the total voltage. Now this is something that we need to pay attention. So for the total capacitance in a parallel circuit is actually CT is equal to C1 plus C2 plus C3. So since, for example, if C1 is equal to 10 microfarad and C2 is equal to 15 microfarad, then our total capacitance CT is just equal to 10 plus 15, so that's 10 plus 15 microfarad, and that is equal to 25 microfarad. Again, this is the difference between resistors or equivalent resistance and equivalent capacitance. In a parallel circuit, it is CT is equal to C1 plus C2 plus C3. The rules for capacitors in series is very much similar to the rules for resistors in series, except for the formula of the equivalent capacitance CT. So for example, the total charge, which is very similar to that of the current, we also have total voltage, and this is something that we need to take note. So for resistors connected in series, this is the law that we need to follow. And this could also be expressed in product over sum rules. So if we only have two capacitors, C1 and C2, then we could solve for the total capacitance or equivalent capacitance as C1 times C2 divided by C1 plus C2. So that's product over sum rules. So if we have three capacitors, we could say equivalent capacitance is just equal to C1 times C2 times C3 divided by C1 times C2 plus C2 times C3 plus C3 times C1. And these are the rules for capacitors in series. And here are the set of rules for capacitors in parallel and capacitors in series as far as charge, voltage, and equivalent capacitance is concerned. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.